Welcome back to Control System Lectures. As always, if you have any questions or comments on what I'm about to say, please leave it in the comment section below and I'll address it. In this lecture, I want to present an introduction to frequency response methods, and in particular, I'm going to describe the Bode plot, how it's generated and used to visualize the frequency response of a system across the entire spectrum. I want to start by explaining another benefit of an LTI system. If you design a linear time invariant system, then there's only a limited number of mathematical operations that you can use. When building an LTI system, you can only use one is multiplication by a constant, the second is differentiation of the input signal, the third is integration of the input signal, and the fourth is adding two inputs together. Now you can always do division by multiplying by the reciprocal, and you can also subtract by adding a negative number. You might be wondering why it's important for me to start this lecture this way, and why bring up the fact that a linear system can only consist of these 6 operations. The answer is that when you subject a sinusoid to these operations, it doesn't change shape. And part of not changing shape means that it also won't change frequency. A sine wave input will always generate a sine wave output of the same frequency. In fact, the only two differences possible between an input sine wave and the output sine wave that's generated is the amplitude, which is the height of the sine wave, and the phase, that is, shifting the sine wave in time. In fact, the sine wave is the only repeating waveform that doesn't change shape in a linear system. You can see here graphically what it means to change in amplitude and also to shift in phase. Let me give you a quick example so you can see what I mean. If we take an input sine wave and subject it to these two separate paths, the upper path is just multiplying it by a constant 2, and the lower path is integrating it, and then summing them together produces the output. If we make the input a pure sine wave of frequency 1/2 radians per second, then we could just calculate mathematically what the output would be. I'd like to make a quick note about frequency. I'm going to refer to frequency in units of radians per second, but this is proportional to hertz. So you can use either in this example. Alright, back to solving this mathematically. The output would then be the upper path, which is a gain of 2 times the input, plus the integral of the input with respect to time. We can simplify this further by just taking the integral in the second half of the equation. Now, in order to interpret this from here, we're going to need some help from some trig identities. Now, I didn't remember this. I had to actually go look this up. But this trig identity that I'm going to be using is a sine of x plus b cosine of x equals the square root of a squared plus b squared times the sine of x plus rho, where rho is equal to the arctangent of b over a. Now, of course, this is only true if a is greater than or equal to 0. So let's apply this trig identity to our problem. In our case, a is equal to 2 and b is equal to -2. So the change in amplitude of the sine wave is just the square root of 2 squared plus 2 squared is the square root of 8 times the sine of 1/2 t plus the arctangent of 2 over -2, which is the arctangent of -1. If we write this in decimal format, this is just equal to 2.83 times the sine of 1/2 t minus 0.785 radians. Now, it should be obvious from this example that the sine wave that we input into the system is still a sine wave on the output. However, the amplitude has increased from 1 in the original input to 2.83, and that's the change in amplitude, and the phase has been shifted by 0.785 radians. Notice also that the output has the same frequency as the input, which is 1/2 radians per second. Now you could draw the input and the output in the time domain, and it would look something similar to the graph that we've done above. And that would work if you were only concerned with the response to a single frequency. However, more often than not, you're going to be interested in the whole frequency spectrum. So how can you visualize the gain and phase shift across the entire spectrum? Well, one way to do that is with the Bode plot. The Bode plot allows frequency response information to be displayed graphically on 2 separate plots, one for gain and one for phase, both of which are plotted against frequency on a logarithmic horizontal axis. But there's a caveat to plotting amplitude gain on a Bode diagram. We don't just plot the magnitude of the gain directly. First, we have to convert it into power, and then we represent the power gain in decibels, which is a logarithmic unit. To convert the amplitude to decibels, you first take the log base 10 of the ratio of amplitudes and then multiply it by 20. If you're confused about where this equation came from, let me just give you a quick history on decibels. When Bell Telephone Laboratories was trying to quantify loss in audio levels through telephone circuits in the early 20th century, they needed a unit of measurement and one that could cover a large range of audio power differences. Because the ear responds to sound pressure logarithmically, using a logarithmic scale corresponds to the way humans perceive sound. They created a measurement called the transmission unit, TU, where 1 TU equaled 10 times the log base 10 of the power loss, and this was chosen because it approximately was the smallest power attenuation detectable to the average listener. Now, to honor Bell Labs founder Alexander Graham Bell, they later changed transmission unit to decibel, or 1/10 of a bell, where bell is just the log base 10 of the power ratio. So to get from bells to decibels, you have to multiply by 10. Also note that power in a sine wave is proportional to the square of the amplitude of the sine wave. So now we can write the decibel equation with respect to amplitude squared, which is 10 log base 10 of the amplitude squared. And just because of the properties of logarithms, the exponential 2 just becomes multiplication, and you get 2 times 10, which is 20. So let's get back to plotting on the Bode plot. If we convert the gain from amplitude into decibels, we can plot the gain for that frequency omega. And for omega of 1/2, we can calculate the gain to be approximately 9 decibels. So on our gain plot, we could find where 9 decibels would be on the vertical axis, and where 0.5 radians per second would be on the horizontal axis, and put a little x there. You can do the same for frequency, but you first have to convert 0.785 radians into degrees, because it's traditionally shown in degrees, and that's -45. This is the frequency response for a single sine wave. But remember, we're interested in plotting the gain and phase across the entire spectrum. So instead of running through the example above an infinite number of times, each at a different frequency, we could have just set it to a variable like omega and solved the system for any frequency. So if we had done that and we had a lot of time, we could have plotted a gain and phase plot that looks something like this for our particular system. And with the exception of being time-consuming, for this simple example, solving the response to the sine wave input was relatively straightforward. Well, except for having to remember that crazy trigonomic identity from earlier. There is a way of solving this without having to remember those identities and still produce the same relationship with frequency, and that's by referring to the system's transfer function. If we take the Laplace transform of the system above, the gain of 2 stays at 2, and the integral becomes 1 over s. Now writing the transfer function for a system like this can be done. The output y of t is equal to 2 times the input u of t plus u of t divided by s. A few algebraic steps here and you can solve for y of t over u of t, which is the transfer function, which is equal to 2s plus 1 divided by s. Recall that the Laplace transform s is a complex variable, sigma plus j omega. However, when we're talking about frequency response of a system, we are talking about the steady state response. That is, once all the transients have died out, or in other words, when the exponential term sigma is 0. So for steady state behavior, s just becomes j omega. Steady state phase and gain can be calculated directly from a transfer function by setting s to j omega. That makes the transfer function become 2 plus 1 over omega j, where 2 is the real component and 1 over omega is the imaginary component. If we then plotted these real and imaginary components on a real and imaginary axis, then we can calculate gain and phase geometrically from this plot. So here our real component is 2, and for omega of 1/2 from our example above, 1 over omega would also be, it's -2. I'm sorry, I made a mistake here. This 2 plus 1 over omega should actually be a minus because j times j is -1. So it's -2 on the imaginary axis for omega of 0.5. And if we draw a line from the origin of the axis to that point, then the length of the line is the gain of the system. And the length can be calculated by just taking the square root of the real component squared plus the imaginary component squared. This is just the Pythagorean theorem. And the phase is the angle between that line and the positive real line. And you can solve for this using the arctangent. I'm using arctangent 2 in this case only because it keeps track of the sign of the inputs, and so you don't have to worry about whether A is positive or negative like we did up above. So again, the length of this line is the gain, and the angle off the positive real line is the phase. So you can see in this example that the real component doesn't change with frequency, only the imaginary component. And if we sweep through frequencies from near zero all the way up to near infinity, you can get a visual understanding of what the gain and the phase are doing for this particular system. At omega of near zero, the imaginary component is almost infinite. And at an omega of near infinity, the imaginary component is near zero. And if you drew that red line from the origin, starting with omega of 0 down at near infinity, which would be a near vertical line, infinitely long, you would see that they would get shorter and shorter and shorter and shorter, and finally ending with a length 2. If we go back up to our plot, you can see that's exactly what the gain is doing. The limit as frequency approaches infinity goes to 6 dB, which is a gain of 2. And off to the left, as frequency approaches 0, the gain goes off to infinity. Also, if you look at phase here, you can see that phase starts out at -90 degrees and then goes to 0 degrees. And again, that's exactly what our plot is doing. And that's how you can represent a large amount of frequency response data through a system. In fact, that's exactly how a graphing program such as MATLAB would calculate the Bode plot from a transfer function. Doing this by hand, though, still seems like it would take a long time. But luckily, there is yet another way to graph the frequency response across the spectrum. And not only is this a much faster way, but it also gives you an intuitive understanding into the frequency response of the system, and you do this only by looking at the transfer function. By following a few rules of thumb, you can graph the Bode plot by hand using straight line representations, and I'll show you that in the next video. For now, as always, thanks again for watching, and don't forget to subscribe.